We have the function f of x equals 100 times 1.05 to the x, where x is the number of years. The initial amount is 100, and f of x is increasing by 5% per year. So in the previous video, we used this for compound interest, but this would be interest that is only compounded once a year. In real life, interest is compounded more often, and we use this formula. So the 1 here represents 100% of the initial amount. R is what banks call the APR, or annual percentage rate. But N is the number of times per year the interest is compounded. So you can think of it as for each period of compounding, the interest rate is the annual percentage rate divided by N. And then the number of compounding periods is the number of times it's compounded per year times the number of years. Let's do a couple of examples. So if my principal is $100, I put it in the bank for 1 year, and it's compounded 12 times at 18%, then each period I get 18% divided by 12, and there are 12 periods. And you calculate it, and you end up with $119.56. So you started with 100, you ended up with 119.56. So the amount of it increased was 19.56%. This is called the effective rate. So the annual percentage rate is 18%, but that's not the actual rate that you earn. And then just for your information, the periodic rate, that's 18% divided by 12. If you have a credit card, this is the way they display the periodic rate in the form of a decimal. So the decimal 0.015, which is 1.5%, is the periodic rate. Now you would think if the interest was compounded more often, you'll get a lot more money. Well, let's find out. When banks compound the interest daily, they use the number of days per year as 360. So if we do the same example with the initial amount of $100 for 1 year, 360 days at the same interest rate, my periodic rate is 18% divided by 360, and the number of periods is 360. And I end up with $119.72. So the effective rate here is 19.72%. You can see that it's only slightly higher than if the interest is compounded once per month. What would happen if the interest is compounded continuously? Well, that would mean that the number of compounding periods would approach infinity. Notice we didn't use the equal sign because a number can never be equal to infinity. So let's just look at this part of the graph, 1 plus, and we'll replace the r with 1 for now, 1 plus 1 over n to the n power, and we'll just plug in bigger and bigger numbers for n. And hopefully we can see what happens when n gets closer to infinity. Well, if you plug in 1, you get 2. If you plug in 10, you get 2.5. If you plug in 100, you get 2.7. At this point, you can see that if you round up, they'll both be equal to 3. So these two numbers agree to the ones place. If you plug in 1,000, Where do they round off to? These two agree to the tenths place. If you plug in 10,000, these two numbers will agree to the hundredths place. If you plug in 100,000, then the two numbers will agree, which means they're equal to the same number if you round off to the thousandths place. So if we plug in bigger and bigger numbers, this is said to converge because it gets closer and closer to a particular number. If n goes to infinity, it gets closer and closer to a particular number that has a special name. This is called Euler's number. And we use the symbol E. So if we take the part of the formula that includes R and you put in bigger and bigger numbers of n, as n approaches infinity, this approaches e to the r. So the formula for interest compounded continuously is just the initial value times e to the rt. Continuous rate of 8%, let's say we're just talking about years. So if something is increasing at a continuous rate of 8% per year, e to the 0.08 is 1.0833, so that's 100% plus 8.33%. So a continuous rate of 8% is the same as a periodic. In this case, we were talking about years. Each year, it would increase by 8.33%. If something is increasing at a continuous rate of 15% per year, e to the 0.15 is 1.162. That 1 represents 100% of your initial value. So something that's increasing with a continuous rate of 15% is increasing with a periodic rate of 16.2%. If you have something that's decreasing with a continuous rate of 9%, e to the minus 0.09 is equal to 0.1939. So if you have a continuous decreasing rate of 9%, that's the same as 100% take away 0.9139. So that's decreasing by 8.61% per unit of x. You can think of this as the effective rate. When do you know which form to use? Well, if you're given a % rate of change per unit of x, then you use the basic form. If it's an increasing function, then the rate is positive. If it's a decreasing function, the rate is negative. But if you're given a rate of change and it's called the continuous rate or the relative rate, then you use the form with a base of e. And again, if the rate is positive, then it's an increasing function. For a decreasing function, the rate will be negative. So for example, initially there were 200 bunnies that were increasing by 8% per year. How many bunnies will there be in 10 years? So we're just given the percent, and we're not given the words continuous or relative. So we just use the regular form. This is increasing, so we use positive 8%. My initial value is 200. So the function is going to be 201 plus 0.08 to the x. And to find out how many bunnies there will be in 10 years, we put 10 for x, and we get 432 bunnies. Initially, there are 500 grams of the radioactive substance polonium, which is decaying at the continuous rate of 9% per year. How much polonium will remain after 50 years? Well, because the rate is given as a continuous rate, then we use the E form. Decaying is the same thing as decreasing, so the rate will be negative. So our initial value is 500, and the function is e to the minus 0.09 times the number of years. So to find out how much polonium will remain after 50 years, we plug in 50. So that's 500 times e to the 0.09 times 50. And we get approximately 5.6 grams remain.